Okay, let's dive in. Imagine this. A substance so cold, it boils at minus 162 degrees Celsius. Minus 162.
Incredible, isn't it?
And it's being shipped across oceans in these absolutely massive vessels. Now, think about the sheer engineering, the precision needed to safely move thousands of cubic meters of that super chilled liquid.
Yeah, it's quite a feat.
That's exactly the hidden world we're exploring today. We're talking about the unsung heroes of global energy. Cryogenic cargo pumps on LNG vessels.
It's a really fascinating area. And, the global energy market relies more and more on liquefied natural gas, LNG, as a cleaner fuel source.
Right.
But getting it from A to B, from the liquefaction terminal to the regasification plant, well, it's anything but simple. The basic challenge is huge. How do you safely, efficiently transfer a fluid that can make steel brittle that vaporizes with even a tiny bit of heat?
It sounds incredibly difficult. To help us unpack all this, we've been digging into some comprehensive guides, things like cryogenic cargo pumps, operations on LNG vessels, and the complete guide to cargo pump operations.
Good sources. Very detailed.
Our mission here, for you listening, is to give you a shortcut, really, a way to get up to speed on these vital components. We're going to uncover some surprising facts and just the sheer ingenuity behind it all.
Yeah, get ready for some real aha moments, I think.
So, okay, beyond the cool engineering, why should you, our listener, actually care about some pumps on an LNG tanker? What's the bigger picture here?
Well, fundamentally, the integrity of the entire global LNG supply chain, it literally hinges on these pumps working perfectly.
Really? The whole chain?
Pretty much. Think about it. Any significant glitch in their performance, any deviation, it can cause massive operational disruptions. We're talking ships stuck in port longer than planned.
Delays.
Exactly. Delays, problems discharging. All of that translates directly into big economic penalties for the ship operators. Demurrage costs can be substantial.
And it's not just about the money for the operators, is it? You've got safety concerns, environmental aspects too.
Absolutely. That's critical. Yeah. You're handling a highly volatile substance at an extremely cold temperature, minus 162 C. So naturally, you need the absolute strictest safety procedures.
To prevent what? Leaks?
Leaks, overpressurization, material failure, any of which could be, frankly, catastrophic. And then there's the environment. Inefficient pumping. It increases something called boil-off gas, or BOG.
BOG, that's the stuff that just evaporates.
That's right. Natural gas vaporizing because heat gets into the tanks, and that's methane escaping a really potent greenhouse gas. So making sure these pumps run optimally is actually vital for environmental compliance. It helps LNG live up to that cleaner fuel idea.
Okay, the stakes are definitely high. Let's get into the engineering challenge then. How on earth do you build a pump for something so mind-bogglingly cold? What materials can even survive minus 162 degrees without just shattering?
Yeah, this is where the material science gets really interesting. Your standard engineering materials. They become incredibly brittle. They lose all their toughness at cryogenic temperature.
So what's the solution?
The key is using special types of stainless steel, austenitic stainless steels, specifically grades like ASI 304. These materials are chosen because they keep their impact toughness way down, even to minus 196 Celsius.
Wow.
But materials are only one piece of the puzzle. The way LNG itself behaves as a fluid, the fluid dynamics, that brings its own unique challenges.
Fluid dynamics. Okay, so how the liquid moves. What's the main challenge there beyond just the cold?
Well, LNG has very low viscosity. It flows very easily, almost like water. And crucially, that very low boiling point we mentioned, this combination makes it highly susceptible to something called cavitation.
Cavitation. I've heard that term is bad for pumps, right?
Very bad. It happens when the pressure inside the pump drops below the LNG's vapor pressure. Tiny bubbles of vapor form. Basically, boiling happens locally.
Okay.
Then, as these bubbles move into areas of higher pressure within the pump, they collapse violently. These collapses create tiny shock waves that are incredibly destructive. They cause noise, vibration, and can actually erode the pump components away.
So the pump needs to be tough for the cold, but also designed to stop these destructive bubbles forming. How do they do that?
Exactly. And it leads to some really clever design features. To deal with cavitation, pumps often have what's called an inducer.
Inducer.
Think of it like a small screw-shaped propeller right at the pump's inlet. Its job is to gently boost the pressure of the incoming LNG just before it hits the main impeller. That little pressure boost helps stop those vapor bubbles from forming in the first place.
Smart.
And even more significantly, these pumps are almost always deep well pumps. This design is a real game changer.
Deep well, what does that mean?
It means the entire motor and the pump's impellers are located right down inside the cargo tank, submerged in the LNG itself.
Inside the tank, with the supercooled liquid.
Yes. And that solves several problems at once. First, it completely eliminates the need for complex shaft seals running from the deck down to the pump. Those are always potential leak points. And second, critically, the LNG flowing through the pump actually acts as the coolant for the electric motor windings and the lubricant for the bearings.
So the cargo itself keeps the pump working.
Precisely. It's a self-contained, self-sustaining system designed for that extreme environment. Really ingenious.
Okay, so we have these incredible deep well pumps, special materials, clever features like inducers. But you mentioned it's usually not just one pump working alone, right, as part of a bigger system.
That's absolutely right. You can't think of it in isolation. The whole setup is a sophisticated network for managing the cargo. You've got your main deep well pumps, sure, for the bulk discharge, but you also have smaller, dedicated stripping pumps. Their job is to get out that last bit of liquid from the bottom of the tanks. And then there are spray pumps used for things like cooling down the tanks before loading or managing tank pressure.
So multiple types of pumps doing different jobs.
Exactly. And they're all driven by electric motors, often using variable speed drives, VSDs.
VSDs that lets you control the speed.
Precisely, which gives you incredibly fine control over the flow rate. That's crucial for efficiency and managing the process carefully. So the real question becomes, how do you orchestrate all this complexity? How do you make it all work together smoothly and safely?
Yeah, I'm guessing it's not just someone flipping a bunch of switches and hoping for the best. What kind of control systems are we talking about here?
Oh, definitely not. Modern LNG cargo operations are heavily automated. At the heart of it, you'll find PLCs, programmable logic controllers, or sometimes larger DCS, distributed control systems.
Okay, the brains of the operation.
Sort of, yeah. They manage everything. The precise sequence for starting and stopping pumps, adjusting speeds with those VSDs, even handling complex emergency shutdown procedures if something goes wrong.
And how does the crew interact with that?
All the information flows back to the cargo control room, the CCR. You've got HMIs, human-machine interfaces, basically complex screens showing real-time data from hundreds of sensors all over the system. Temperature, pressure, flow rates, pump status, motor current, vibration, everything.
So the operators are watching all this data stream in.
Constantly. And the system has layered alarms. It'll alert the operators to any deviation, any anomaly, hopefully well before it becomes a critical problem. It's all about using technology to boost safety and efficiency.
But even with all that sophisticated automation, it sounds like the human element, the operator, is still absolutely essential.
Oh, completely vital. The automation supports them, but it doesn't replace their judgment and vigilance.
So what are the key steps, the main operational protocols these highly trained people follow? How does a cargo operation actually unfold?
It's a very meticulous process, broken down into distinct phases. First up is pre-operational readiness. Think of it like the pre-flight checklist for a spacecraft. It's that critical.
Okay, what does that involve?
Rigorous checks, making sure all the valves are lined up correctly, calibrating sensors to ensure they're reading accurately, detailed electrical checks on the pump motors, and crucially, confirming the inert gas systems are ready. That's usually nitrogen, used to keep air out and prevent explosive mixtures. An invisible safeguard, but absolutely vital.
Got it. Checklist complete. What's next?
Then comes operational planning and execution. This is where they map out the entire discharge. Defining the sequence for starting the pumps, setting the target discharge rates, figuring out how they'll manage the pressure in the tanks as the liquid level drops.
And the actual operation.
It starts with a very careful, gradual cool down of the discharge lines and the pumps themselves, usually using LNG vapor. This prevents thermal shock. You can't just hit cold metal with minus 162 liquid suddenly.
Right, that makes sense.
Then, during the discharge, the operators, aided by the control system, are constantly monitoring and adjusting. Using the VSDs to keep the flow steady, watching for any signs of cavitation, and actively managing that boil-off gas to keep tank pressure within safe limits. And they always have contingency plans ready. What if a pump trips? What if there's a leak? They've drilled for it.
Sounds intense. What happens after the cargo is offloaded?
That's the post-operation phase. Once the main discharge is done, those stripping pumps kick in to remove as much of the remaining liquid heel as possible. Then, the tanks and lines are usually purged with inert gas, nitrogen again, to get rid of all the methane vapors. Makes the system safe for any potential maintenance.
And the pumps.
The pumps are isolated, allowed to warm up gradually back to ambient temperature again, avoiding thermal stress. Then they get inspected carefully. Any leaks, unusual noises during operation, signs of wear, All the data from the operation flow rates, pressures, running hours gets logged. That informs future maintenance planning. It's a continuous cycle, really. Vigilance, operation, inspection, planning.
It definitely sounds like an environment where learning by doing or trial and error is absolutely not an option. The sources we read really hammered that home.
You've hit the nail on the head. That's a critical takeaway. The entire philosophy is built on 3 core pillars. Safety first, always. Know your system, inside and out. And procedural discipline, following the established rules meticulously.
And relying on the automation isn't enough.
No, that's a dangerous trap, actually. Believing the automated system is foolproof. Our sources point this out clearly. Yes, the IAS, the Integrated Automation System, provides vital safety interlocks and trips, but those alarms, they should be your last line of defense, not your first sign something's wrong.
So the operator needs to be ahead of the system.
A truly vigilant, proactive operator is constantly watching the trends. Subtle changes in motor current, maybe a slight dip in discharge pressure. They're spotting potential issues developing long before any formal alarm sounds. They're the ultimate command authority, not just watching a screen.
Right. So given all that, what are some of those absolute golden rules? The things operators absolutely must live by to protect these expensive, critical machines and, of course, the cargo.
The sources are very clear on several non-negotiables. These really encapsulate that deep system knowledge, for instance.
Okay.
Number 1, the never run dry rule. We talked about LNG being the coolant and lubricant. Well, running a pump without enough liquid flowing through it will cause it to overheat very quickly. Result, catastrophic failure. Simple as that.
Makes sense. What else?
Minimum continuous flow. You must never operate a pump continuously below a certain rate. The figure often quoted is around 633 cubic meters per hour. Running slower than that for long periods essentially starves the pump of cooling and lubrication. It causes significant damage over time.
Okay, avoid running too slow.
Then there's an interesting one about efficiency, optimal flow. It's actually far better for both efficiency and pump lifespan to run one pump at its design sweet spot that's around 1,850 cubic meters per hour near its best efficiency point rather than running 2 pumps each at half that speed.
So one pump working hard is better than 2 loafing.
In this context, absolutely. It maximizes efficiency and minimizes wear and tear. Then there's restart discipline. Starting these big motors draws a huge amount of current, which generates heat in the windings.
Right.
So the rule is strict, a maximum of 3 consecutive start attempts. If it doesn't start by the 3rd try, you must wait 30 minutes for it to cool down, mandatory. And no more than 4 starts total are allowed within any 1-hour period for any single pump. You have to let that heat dissipate.
Wow, very specific. One more.
How about handling shore delays? This is a practical one. Let's say the receiving terminal asks for a temporary stop in pumping, but your tank levels are already quite low, say below 1.5 meters. The absolute rule is, do not stop the pump.
Don't stop, even if they ask.
Correct. Instead, you keep the pump running, but redirect the flow, recirculating the LNG back into the same tank it came from. This avoids a potentially damaging restart when the suction level is already low, which could easily cause cavitation or run dry issues.
Those rules really show that true mastery isn't just pushing buttons. It's about understanding the why behind every single parameter, every procedure, and knowing how to adapt safely.
Exactly that. The hallmark of a really experienced expert operator is that proactive monitoring, using all the data from the IAS not just to react but to anticipate, spotting those subtle deviations. Knowing, for example, to gently throttle the discharge valve before a low motor current trip happens during stripping that final phase to prevent cavitation damage, that's the difference between just operating and truly managing this system.
So let's try and wrap this up. What does this all mean? This deep dive has shown us, I think, that cryogenic cargo pumps are this amazing intersection of precision engineering and incredibly meticulous operations.
Right.
It's a world defined by extreme temperatures, advanced materials, and just an unwavering focus on doing things exactly right every time for safety and efficiency.
And connecting that to the bigger picture, the journey to being truly excellent in this field, it never really stops. It's constantly evolving with new technology, using data more effectively for decisions, and continuous training and development for the crews. It's about shifting from just being a component operator to becoming a true system manager, someone who deeply understands the why behind every single how.
And as you think about that, consider this. The safe, reliable flow of huge amounts of energy that underpins our modern lives. quietly depends on individuals mastering these incredibly complex systems. Systems operating at temperatures colder than you can really imagine, often thousands of miles out at sea.
It's quite something when you put it like that.
It really makes you wonder, doesn't it, about all the other critical, highly specialized, often invisible systems that are just quietly working in the background, making our world function. How much do we all rely on this kind of hidden mastery, the expertise that just makes everything else seem normal?
A lot more than we probably realize.
Perhaps this deep dive will encourage you to look around. Look for those unsung heroes and intricate systems working away behind the scenes in your own world.